Welcome, Mindsetters, grade 12s. It is a Tuesday. We had Tracy, now we have TK. So I have triple T's on a Tuesday. How amazing is that? TK, how are you doing?
Good, how are you, Lenny?
I'm good, thank you. So
Yeah.
what are we doing for the Mindsetters today?
Today we're going to do some nice revision on mechanics. So it's a very exam question packed lesson that we're going to look at. So it's a good revision for them.
All right, I'll send you to the board and you can just prepare for the lesson.
Okay.
Grade 12s, our lesson is brought to you by Macmillan. So thank you so much for sponsoring us, Macmillan. We are doing mechanics revision, guys. So if you guys struggle with that section, TK is here to help you out. Remember, we do have Facebook page. Our Facebook page is facebook.com/learnextra. You can hit us up on Twitter. It is @learnextra. Remember, if you want to download all the show notes, the videos, the schedules, if you want to know how to order DVDs, books, and everything else that's got to do with mindset and learning and revision and exams and all that great stuff, guys, you just need to go onto learnextra.co.za/live, where you can get all your learning materials, because we're here to help you study and become the greatest students in this life. So I'll hand it over to TK to give us the lesson.
Thank you, Lenny.
All
Like I said, we are dealing with revision on mechanics today. So when we're talking mechanics, you will remember we're looking at things like graphs of motion. We're looking at equations of motion. We're looking at, if you remember very well, we should be looking at things like, basically, we're talking motion. Let me just say motion. And in this lesson, specifically, like I said, we're looking at graphs. We're going to look at momentum. We are also going to look at the work energy theorem. I know that this work energy theorem does give you a lot of problems, guys, and please go with me in this lesson, listen attentively, concentrate, work with me, let you get the necessary skills that you need to answer those questions without any difficulty, because I bet with you that question will be there in your June exam, it shall be there in the preliminary exams, and those questions will also be there at the end of the year. So here is a good chance for you to have some revision based on this section of your work here, mechanics. Now, starting with question 1. In question 1, we're specifically going to talk graphs of motion. Okay? I've got a question here that is based on graphs of motion, and this question is from the November 2008 paper 1. Now, this was the very first time when we started with the new syllabus, and it's a very nice question that is there, and we're going to see how you are supposed to answer questions based on graphs of motion. One thing I need to mention, though, right from the start is, once you have got a graph to work from, you answer based on that graph. So questions are given to you, and the questions are based on that graph. Try by all means to confine yourself to the graph and see how you can use the graph to answer those questions. And we are going to learn some of the skills and some of the necessary knowledge that is required for you to answer questions based on graphs. Now, this question here says, a boy stands at the edge of a high cliff. He throws a stone. Now, he is throwing a stone. He throws a stone vertically upwards with an initial velocity of 10 meters per second. Now, these details are important. The stone then strikes the ground at a point below the cliff after 3.5 seconds. Now, that is time. It's very important. The velocity time graph, so you are given a velocity time graph. This graph below was obtained from measurements made during the motion of the stone. Okay? So this graph here is a result of the motion of the stone. Now, the first question that we need to answer says, determine the height of the cliff. Find how high the cliff is, or determine the height of the cliff from which the stone was thrown. Okay? Now, I think here we should be starting with another question before that. That is much, let me see what I have here. There's something that is a bit confusing here. Now, let me just do something with this graph, okay, before that question, because that's somehow a big one of a very, very challenging question that I feel we shouldn't start there. We should have started somewhere else before that question. But let me just have a look at this graph here and try to unpack it for you. Now, the boy is throwing a stone upwards at a velocity of 10 meters per second. Now, if I look at the shape of the graph, you can see that the shape of the graph is such that it is a straight line slanting with a negative slope. All right? Now, what does that mean if I look at this graph? It tells me that whoever drew this graph took the direction upwards of the stone to be positive. Because I am seeing that this velocity here from 10 meters per second downwards to getting to 0 meters per second is such that it shows that it is positive in that sense, but immediately after the stone has gone to its highest point, we have got negative values here for the velocity. Now, it tells me that going upwards was positive, and therefore, coming downwards is always taken to be negative in this situation here. Now, if going upwards is positive, all right? If going upwards is positive, going downwards is negative, it means now that I've got directions for all my vector quantities that are here. Remember, when I talk velocity, I need to know what the direction is. When I talk acceleration, I need to know direction. When I talk displacement or change in position, I need to know the direction. Now, the graph here is such that up is taken to be positive and down is taken to be negative. Now, the stone goes up. When the stone reaches its highest point, all right? At the highest point, we know that the stone is going to stop momentarily and then begin to drop down or come down, all right? What does it mean for that point? It means that at that point, the velocity of the stone is 0. And therefore, it is at this point here when the stone reached its maximum height. Okay. Now, as the stone comes down, remember that the down is negative, given the fact that up is taken to be positive. So, as the stone begins to come down, its velocity is negative, and therefore it had to be in the negative sense like that. Okay. Now, what can we get from the graph, from a graph of velocity versus time? One thing we need to be aware of, before we answer that question, allow me to talk about other things here. From a velocity time graph, we need to know that one, if I find the gradient of that graph, that gradient is going to give me, sorry about that, that gradient is going to give me what we call the acceleration. So this is one thing I can get from a velocity time graph. And I'm going to show you how we do that. Second, we can get the displacement. Okay, we can get the displacement or the distance moved. But in this case, I want to stick to displacement because we're talking vectors here, things going up and down, projectiles, it's displacement. So from this, how do we get the displacement? Up there we said when you get the gradient, it gives you acceleration. Then how do we arrive at the displacement? To get the displacement, we find the area enclosed by the graph or under that particular graph. Now let's then try and see what we can get from this graph here. If you go back to this graph, from the graph, I can be able, therefore, to find the acceleration of the object. Like I said to you, acceleration will be given by the gradient of the graph. And if you look at this graph here, this is a graph of velocity versus time. So on your vertical axis, you've got velocity. On your horizontal axis, you've got time. So the gradient of that graph will be change in the vertical, which is what? Change in velocity divided by the change in time, which is the change in the horizontal here. So down here, we've got time in seconds, all right? And then let me just put this as, this is 1, this is 2, and that is 3, okay? 3 seconds. And therefore, if this is 1, then halfway here, it means I've got 1,5, I've got 0,5, and then between 1 and 2, I will have 1,5. I'm just putting these readings here just to help you understand how some of these calculations we're going to do come from, okay? So that will be 3.5, like that, okay? So from this graph here, now I want to find out what that gradient is. And remember, what does the gradient of a velocity time graph give us? It gives us the acceleration. Let's work it out. If I want to get the acceleration, for example, between time 1 second and time 2 seconds, or maybe let me just use between 2 seconds and 3 seconds. Just want to use that. Now, what is the time here? The time there is 2 seconds, and what is the velocity at this point? The velocity at this point is this one, and that is minus 10, okay? If you come down here, you've got the time value to be 3 seconds, and what is the velocity value? The velocity value is this one here of minus 20, okay? So if I want to work out this gradient here, I will then say this will be equal to, let me just change the color so that we can all see what this is coming from. So change in velocity, it changed from this point to that point. It was minus 10 here to minus 20, so it will be minus 20 minus minus 10. That is the change in velocity divided by the change in time. It changed from t 2 seconds to t 3 seconds. So it will be 3 minus 2. So what do I have at the end? Minus 20 minus minus 10. This will be minus 20 plus 10, which is minus 10. Divided by 3 minus 2, it's a 1. So this gives us 10 minus 10 meters. Now the unit, per square second. Why per square second? Remember that here you've got meters per second, and you've got meters per second there. Allow me to write it like that. Don't have much space. And then you're dividing by, down here you've got seconds. So that end up with meters. I'm giving you meters per square second there as the unit of acceleration. Okay, and then now, if for example, I want to know how this stone moved. I can actually describe this motion here. One other thing I can tell is I can actually use time to tell the position of the stone at whatever point. For example, I can be able to say that at the time 0.5 seconds, which is this point here, 0.5 seconds, the stone was moving at 5 meters per second. Okay? I can tell that because that is the speed at which it was moving. At the same time, there is another point where this stone was again moving at 5 meters per second, but in the opposite direction, which is this point here. And this 5 meters per second there. And then I can tell the time where, I can actually tell the time as well as to at what time was it again moving at 5 meters per second. Now this time here was 1.5 second. It is that time there. So at 1.5 second and at 0.5 second, both these times the stone was moving at the same velocity of 5 meters per second. The only difference is that at one point it was still going up, in the other point, or at the other point, it was now coming down. Okay, so we can tell quite a lot of things here. Another thing that we can get from a velocity time graph is displacement, or how far the object has moved. Now, how do we do that? Like I said, you work out the area enclosed by that particular graph there. So I will come back to this graph, and then we look at that area and we see how you come up with the displacement, how far that object or that stone has moved.
All right. Guys, hearing all this stuff is just taking me back to matric, when we used to do all these graphs and just work out all that stuff. It used to make my head a bit sore, but I hope you guys are following and you guys understand. Remember, if you have any questions, our Facebook page is there for you. Don't go anywhere. All of this is up for grabs, guys. So stay tuned and watch your screens. Don't even go for a little break, guys. Just stay glued to your screens for After Earth. Welcome back, Mindsetters. I hope you're just as excited as I am about this After Earth competition. Remember, guys, we are giving away a goodie bag, which consists of, guys, check this out, a pen that lights up blue, guys, when you just, click it there, when you go click the pen, when you do that, it lights blue, guys. So that is just too awesome. It's got a pen. We have a nice sweatband here with a nice little pocket to put in your money or anything. Maybe when you're jogging and you need to put in some extra cash for some water or anything. We've got a cool sweatband, personalized After Earth sweatband. We've got this nice notebook, guys. It's got great pages inside, After Earth written inside. If you want to write down notes, for school when you're practicing your maths, your physical sciences, all the calculations, you can write them down here. And we've got this awesome t-shirt that you can win, guys. So it's a goodie bag and 2 tickets. All you need to do, grade 12, is go on to learnextra.co.za/After Earth and enter your code word. Grade 12's your code word for today is aerostatics. I will post it on Facebook, guys. Aerostatics is your code word. I'll post it on Facebook and just give you all the information on our Facebook page. I just like to congratulate Lihlakhonolo Bracket Mokoena. I hope I pronounced that right. Lihlakhonolo Bracket Mokoena, you've won yourself 2 tickets from last night's show. 2 tickets to go watch After Earth. Remember, if you don't have a friend and you need a friend, I can be your +1, hey? Just there, call me, WhatsApp, Facebook, I will come. I will be your +1 to go watch After Earth. Remember, guys, it does come out June 7th here in South Africa. So go check it out. It's an awesome movie. Jaden Smith, Will Smith, doing their thing. Father-son duo. Too awesome. Aerostatics is your code word. After Earth should be in your mind. But right now we'll go to TK, who's going to tell you about velocity, what's this area, all those things, displacement. I did that stuff in matric, guys. It's been 3 years, but I still remember, so I'll take it back to TK.
Okay, thank you, Lini. And then now continuing, like I said earlier on, I tried here to clear out, because I need to talk again on onto this graph here when we're looking at the area. And actually, I'm going to use this question here, question A here, to show you how you make use of the area enclosed by the graph to find how far that particular object has moved. In this case, we're talking about this stone here that was thrown upwards by this boy here. Now, the question here says determine, okay, it says determine the height of the cliff from which the stone was thrown. Now, there is something tricky about this question that you need to understand. Why do I say so? This area here is the area under the graph when the stone was still going upwards. It's not at the point when it was thrown, but it was still going upwards. It then got to the highest point where it stopped a little bit and began to come down. And therefore, I've got another area here enclosed by this graph here. So I'm going to mark this area, okay? I'm going to mark this area here. So let me mark it up to that point. Actually, this fell off the mark there. It should be up to this point there. All right. Now, the two areas, this one here, let me call it height 1. And let me call this one here height 2. And why do I call them heights? Because this stone was actually moving up and down. Now, if I want to know where the stone was thrown from at the top of the cliff there, it means I must know, because this part here, this whole area here, is the whole area from the top of the cliff, or from where the stone turned. So it was thrown from somewhere here, it goes up, then it turned and came down and hit the bottom of the cliff. Now, this area here, H1, talks about that part there. And then H2, on the other hand, this whole area here, or that whole part there, is our H2. That's the H2 height. You will therefore agree with me that if I want to know the height from where the stone was thrown, which is this point here, if I want to only know that part, it means I would have H2 minus H1, okay? That will be the height from which the stone was thrown, because I would be subtracting that part from this part here, this down part here from there. All right. So knowing that the area of, or the area enclosed by a velocity time graph will be giving me that height or that displacement, it means that I can say for H1, I will be concentrating on this triangle here. And if I get the area of that triangle, I will have found how high it moved from the point it was thrown up to the highest point. And if you check there, I'm saying to you, you've got a triangle, and it happens to be a right-angled triangle, so its area can be found by this formula here, half base times height. Now, what is our base? If you check here, it is from 0 to 1. So the base here is 1. The height here is from 0 to 10. So the height here is 10. All right? And therefore, knowing all those reasons or those readings there, or those measurements or those dimensions, I'll be able to say this will be half times the base 1 times the height 10. And therefore, this will be equal to what? It's going to be 5 meters. Okay? Remember, I haven't answered the question yet. I'm still trying to find information that will help me know how to find the height at the point when the stone was thrown by this boy. Now, height 2, on the other hand, height 2, it is again a right-angled triangle, so it will be half base times height. So half times, what is the base for our next triangle here? The H2. It is from here. Let me use a different color here so we see what we're talking about. It is from there to there. All right? So if that is your 0 point, if this is your 0 point, then that is 1, and that is 2, and therefore that is 2.5. So your base is 2.5 seconds, okay, in terms of what we're working with here, which is time. And then you look at what is then my height there. The height is from 0 down to what? Down to 25, to that point. It is this point here. Okay? So it will be half 2.5 times 25. All right? Half 2.5 times 25. Okay? So you work that out. Okay? You can actually make use of the calculator. We do have it here. All right? So let me put it this side because we're working there. So we've got 0.5, which is half, times 2.5 times 25. Okay? And what do we get there? 31.25. Okay? So 31.25. This is meters, like the first one, which is in meters. Now remember, we said to find the height, okay? To find the height from where the stone was thrown, we will then be saying height 2 minus height 1. What is height 2? Height 2 is 31.25 minus height 1 is 5 meters. And therefore, this works out to what? It works out to 26.25 meters. So that is how high the stone was before it was thrown up by that boy. So that is the height from the bottom of the cliff to where the stone was thrown upwards. Okay, I hope you understood that. And then now, let me go back to the graph again, because some people are asking about the issue of directions here. And I think I need to explain it, because you will always go wrong with these problems here if you don't get your directions right. Now, I said to you, when you look at this graph here, you look at the graph, you see that from this point downwards, this is your negative territory of your vertical axis, okay? So this is where you've got your negative velocity. But from here upwards, from there upwards, you have got your positive territory, all right, of your velocity there. So if the stone that has been thrown upwards, we see it decreasing in velocity, coming to 0 there, and then having negative velocity until it hits the ground at that point there, that tells us that at the time it was going up, because this whole part here, it's for going up. At the time it was going up, everything was in the positive. So it means that whoever drew this graph took going upwards as positive. And therefore, that means going downwards is negative. Now, what are we referring to by saying positive and negative? We're referring to every quantity involved there, which is a vector quantity. Velocity, as we're talking about it here, displacement, okay, and then acceleration. For example, when you got the acceleration up there, when we were still trying to calculate for it earlier on and found it to be 10 meters per square second per square second. Actually, that 10 meters per square second, because we found it to be negative, 10 meters per square second. All that the negative meant was that the acceleration is in the downwards direction. So you could actually say this means that you're talking 10 meters per square second downwards if you don't want to have that negative there. Now, it came up with a negative sign because acceleration due to gravity, I think you would know it. It's always downwards. And it is, of course, in line with what the choice of the directions are here on this graph here. So that's how we come up with the directions. Now, let's come down to the next question here. All right? Using the top of the cliff as the initial position of the stone, sketch the position time graph or the displacement time graph for the motion of the stone from its highest point. So only from its highest point until it reaches the ground. In the graph, only indicate relevant time values. Okay? Relevant time values. How do we do that question there? All right? Let's just have a look at it. We know that at the highest point, perhaps we can go back to the graph. At the highest point, we know that at the highest point, the time was 1 second. Okay? This is the highest point here. That is the highest point when the velocity was 0 meters per second. So the time was 1 second. So we need to indicate that time there. All right? We need to indicate that time here on this question here. Now, if I am to draw this graph here, and I have, let me erase this. If I am to draw this graph here, I have my vertical axis there, and I have my horizontal axis there. Ooh. Okay. Vertical axis, all right? And I have my horizontal axis like that. This is my time in seconds, all right? So that's my time in seconds. And this is my position or displacement. So position this side in meters, all right? When the time was 1 second, I know it was the time when I had the highest point reached by the stone, okay? And from the graph again, we can also tell how long the stone took to reach the highest point and to come down. Now, it took 1 second to reach the highest point, and at what time again, all right, did we have the stone reaching a position somewhere where it is passing through the x-axis, perhaps, if you like? What I know is that at the time 3.5 seconds, at this time here, okay, it was right at the bottom of the cliff, okay, right at the bottom of the cliff. So I'll need to extend my x-axis here, I mean my y-axis here, so that I can show at 3.5 there, 3.5 seconds. It is somewhere at the bottom there, and then at the time 1 second, okay, it's when it reached its maximum height. So I can actually say, all right, my graph here will be such that it comes down to a point somewhere there, okay? All right, to a point somewhere there. And at that point, that's when it hits, or it actually strike the bottom of the cliff. So that will be my graph there, the graph of position, okay? The graph of position versus time, right? Position versus time for that particular stone there. All right. Now, one thing we need to know always is that if I'm talking a graph of position versus time when we're talking projectile motion, it is definitely going to be a curve, and that particular curve will be a quadratic curve. It's either going to be in terms of the directions that have been chosen, either you're going to have it facing downwards or facing upwards. But because we're only looking at the section from the top where it reached its maximum height and coming down, so we've got only this part here. You can see there that we can actually have, if we were told to show other sections of the graph, perhaps we're also going to show some part of the graph in that way.
Okay. Mindsetters, if you've just tuned in, remember we are doing mechanics revision, with TK, and our show is proudly brought to you by Macmillan. Career and Daba, After Earth, I'll tell you more about that straight after the break. Welcome back, Mindsetters, from that very short break. Like I said, after the break, I'll tell you about After Earth and Korean Dawa. Most of you are asking me about After Earth and how to enter. Guys, I did say before we went to a break, before we even, like the very first break, I told you about After Earth. All you need to do is go into learnextra.co.za/After Earth and enter the code word, which is aerostatics for the grade 12s. I did post it on Facebook as well, guys, so you have all that information in order to win all these great prizes and 2 tickets to go see After Earth. Korean Daba is at the Santon Convention Center this year from the 20th to the 22nd of June. We will be there, guys, so remember, if you want to meet me, Abraham, Indy, and all your favorite Learn Extra Live presenters, guys, we will be there at the Santon Convention Center. If you want to get more information on what you want to become and what career path you want to take, if you're confused, you don't know if you want to be a lawyer, a doctor, a dentist, an artist, or any of that stuff, Korean Daba is for you, grade 10 to 12. All you need to do is go into koreandaba.co.za and register. It is for free, guys. All you need to do is go onto that website, register yourself, and we will see you at the Santon Convention Center. So TK, take it away.
Thank you. And now I want us to go to question 3, and if we have time, we'll go back to question 2. And the reason why I want us to go to question 3 is because question 3 talks about the work energy theorem, and I know that so many people battle with that one. Let's just have a look at it. Question 3 here says, a worker pulls a crate, okay, of mass 30 kilograms from rest along a horizontal floor by applying a constant force of magnitude 50 newtons. He applies that force at an angle of 30 degrees to the horizontal. A frictional force, now this is important, a frictional force of magnitude 20 newtons acts on the crate whilst moving along the floor. All right, now let's look at the questions here, and there is the diagram giving us a sketch of what is happening here. The first question says, draw a labeled free body diagram to show all the forces acting on the crate during its motion. Now, when we talk of free body diagram, you need to represent that diagram simply by a dot, Okay, so don't redraw that crate there. Just put a dot to represent your object. Okay, now, which are the forces that are acting on this crate here? One force for sure that we can see immediately is the applied force. So let me call it FA, the applied force, which is the 50 Newton force. It is applied at that angle there, which is an angle of 30 degrees. So if you like, can also indicate that. Now, what we also know is that this crate here is on a surface, and every object lying on a surface experiences a force called the normal force. And this force is a force that is acting on the object perpendicular from the surface of the surface where that object is. So this becomes what we call the normal force, Fn. All right. Now, apart from the normal force, everyone should get this one right. The force of gravity on that crate, okay? But then I need to draw it in such a way that the two are of the same magnitude, okay? So this force due to gravity, it's equal in magnitude to that normal force there, but they are acting in opposite directions. The fourth force that I still have to show here is the force of friction, which will be the force in this way, okay? So that will be the force of friction, okay? I can even give the value of that force if it is given to me, but in this case, yes, it is given to me. You've got 20 newtons there as the force of friction there. All right, so you can even show that. Okay, so you get your 4 marks by doing that. Next question, give a reason why each of the vertical forces are doing no work, all right, on the crate. Now, what you need to know is that work is only done by a force on an object if the force and the displacement of the object are in the same direction. Now, if we have a situation where the force acting on an object is perpendicular to the displacement or the direction of motion of that object, that force is doing no work. So the reason why these two forces, it is these two forces that we are referring to, this one, and which is the normal force, and the force due to gravity. Those two forces are doing no work because the two forces are acting perpendicularly or at 90 degrees to the direction or to the displacement of the crate. So those two forces are doing no work to the displacement of the crate. No work is done by these two forces on that crate. Okay? Now the next question. Calculate the net work done on the crate as it reaches point P, which is 6 meters from the starting point. Now, the net work, okay, or work net, should be work done by the applied force, okay? So work done by the applied force, if you like, plus the work done by the frictional force. Sorry about that. So work done by the frictional force. Now, can we begin to see from the diagram which force is doing the work? Obviously, the component of this force here in that direction is the one doing the work. Therefore, that one doing the work there should be the force applied, okay, times the what? That is adjacent to the angle, so it will be the cos of 30 degrees, okay? Now, the frictional force, remember, it's acting in the opposite direction. So this one should be force of friction times the what? Times the cos of 180 degrees, because the angle here is 180 degrees in which this frictional force is acting. So we can then say here, we come down here and say the work net then will be equal to F times the distance moved, remember that is work, times the cos of the angle, so that we get the component of the force that is doing that work, plus the frictional force, or work done by the frictional force, will be frictional force times the displacement moved times the cosine of the 180 degrees. All right, so work that out. This is 50 times distance moved, or displacement is 6, times the cos of what? 30 degrees, plus frictional force is what? Is 20 times 6 times the cos of 180. Okay? And at this point, all we need to do is just to use our calculator and work it out. Okay, how do we do it there? So you've got 50 times 6 times the cos of 30. All right? You can work it out. There's 259.81. So this is 259.81. 259.81. If you work out that, okay, let's just have a look at it. If you work out the frictional section part, you've got 20 times 6 times the cos of 180, okay, times the cos of 180. And what do you get? That is minus 120, right? So minus 120. And what do you get from there? So you've got minus 120 plus 259.81. Okay, and what do you get? We're getting it to be 139.81. So that is 139.81 joules of work that has been done there. Okay, so that's how you solve that problem there. Coming to, okay, so that's what you have there, finding the network there. All right, now let me check what I have here. I think we should be having a few more questions there, but then let's go back to question number 2. All right, let me see if we can do a little bit of question number 2 there with a few minutes that we are left with. Question number 2, it's from the 2010 November paper. It says a steel ball of mass 0.5 kilograms is suspended from a string of a negligible mass. It is released from rest at point A. So we're going to see what point A is here. Let me just show it to you. There is point A. All right. As it passes through point B, which is 0.6 meters above the ground, the magnitude of its velocity is 3 meters per second. So that is point B. That is point B. All right? Ignore the effect of friction and you answer the following questions. Write down the principle of conservation of mechanical energy. Now, what do we know about this? The principle of conservation of mechanical energy says that the sum of kinetic and potential energy, and potential energy remains constant. This remains constant in an isolated system or in a closed system. Okay? So if you don't want to use the word closed, you can use isolated system. So that's what the principle of conservation of mechanical energy says. Then question number B, calculate the mechanical energy of the steel ball at point B. Now, first, mechanical energy is always given by the sum of potential energy and kinetic energy. Now, what is EP? EP is mgh, EK is half mv squared. Okay? Now, going back to finding what the values are here, the height is 0.6 meters, the mass is 0.5 kilograms, and then the velocity at this point here is also given to us, that it is at the height of 0.6 meters, it is moving at 3 meters per second. So we can actually put in those values here to find what the mechanical energy is. So mass is 0.5 times G is 9.8, it's always given to us, times 0.6 meters plus half times 0.5 times 3 meters per second squared, okay? And then we can work it out there, making use of a calculator, right? So 0.5 times 9.8 times 0.6, that's what you have. So it gives you 2.94. Okay, so this works out to 2.94 plus the other part then would work out to 0.5 times 0.5 times 9. 3 squared is 9. I think we can get that immediately. And that is 2.25, okay? So that is 2.25. And you add those two together, you get, so this is plus 2.94. And what do you get? You're getting 5.19 joules. So that is 5.19 joules. Now, I wish we had more time to actually go through the rest of the question and even the other one, but that's how far we can go today. Thank you, Luni.
All right, thank you so much, TK. Mindsetters, thank you so much for tuning in. Guys, when you're writing your exams, just remember to calm down, read the questions carefully, and just do your best in everything that you do. Thank you so much for tuning in, and thank you to Macmillan for bringing us a great show. We'll see you next time, guys.